சரி, சரி, சரி.
அதனால சார் கொஞ்சம் ஓவர் கம் பண்ணிட்டாங்க.
ஓகே. இப்ப அடுத்து நீங்க தான்.
கார்த்திகை மாசம் முழுவதும் மேகம் இருக்கிற இடத்துல எல்லாம் பெய்யுமா? அதனால நாளைக்கு வேற திருக்கார்த்திகை.
ஆமா, நாளைக்கு திருக்கார்த்திகை.
Hello, Kiranji?
Hello?
Yeah, good evening, sir.
Good
Yeah,
evening,
good
sir.
evening. Yeah, I'm ready. Let me know. Yeah.
Yeah, sir.
Hello, good evening, sir.
We'll wait for some
Yeah, good
5
evening.
minutes, sir. Let all the participants join,
Right.
and then we'll start, sir.
Right.
करो चल ठेवले नाही मी ते भांडला
Hello, good evening, everyone. Myself, Professor Deepak Singh. I warmly welcome you all participants on the day 2 of our online FDP program on shaping the future of manufacturing with 3D techniques. I would like to thank you all, the enthusiastic participants on the day 1. Yesterday, we had two highly insightful sessions. Session 1 was delivered by Dr. Guru Prasad Rao sir, focusing on the 3D printing and future avenues, where he shared his valuable perspective on the evolution, opportunities, and the industrial impact of additive manufacturing. On the other hand, the session 2 was delivered by Dr. Datta Parle, where he focused on the materials for 3D printing technologies. He highly demonstrated the different types of materials, their properties, and their adaptability to the various manufacturing sectors. On this day today, we have two existing sessions lined up. The session third, that will be the first session of today, will be delivered by Dr. Y. Ravi Kumar sir on the design of additive manufacturing technologies, whereas the session 4 will be delivered by Dr. Z. Shu on the printing embedded sensors using 3D technology. With this, let us begin the today's session. First of all, I would like to welcome Dr. Y. Ravi Kumar sir. Sir, welcome to our online FDP program, sir.
Thank you.
So, Dr. Y. Ravi Kumar sir is a professor and the head of the department at NIT Warangal. He has experience of more than 26 years in the teaching academics. He holds his BTech from JNTU Kakinda and ME in Computer Integrated Manufacturing from PSG College of Technology and PhD from Osmania University. He completed his postdoctoral research in 3D printing from USA. His research expertise include additive manufacturing, 3D printing, rapid prototyping, and medical additive manufacturing applications. He has published more than 85 plus research papers, guided over 40 plus MTech projects, and produced more than 6 PhD students, and currently supervising many more. He has also held 4 major funded R&D projects worth over 1 crore rupees and has established a world-class metal 3D printing facility at NIT Warangal under the TCube 3. Professor Ravi Kumar sir has granted 1 US patent and 2 Indian patents, and also he has introduced India's first MTech program in additive manufacturing technologies and delivered more than 358 plus talks all over the globe. He is currently the chairman committee of NCAM and a contributor of Wholesaler Reports and recipient of the Young Engineer Award from in 2009. We are very pleased to welcome you, sir, and thank you so much for accepting our invite. Now, sir, session is handed over to you. You may continue, sir. Thank you, sir.
Yeah, thank you for your nice introduction. So, first of all, let me share my screen.
Yes, sir.
Is my screen is visible to you?
No, sir. Not yet, sir.
Now, check it. Hello.
Sir, your screen is not visible.
Share window.
Yes, sir. It is visible now, sir.
Yeah, thank you. So, first of all, let me thank the organizers of this FDP, in particular Professor Kiran Bole and his team from Sardar Patel College of Engineering, and of course the AICTE ATAL for the sponsor of this FDP. So my talk will be on the design aspects of additive manufacturing. So yeah, I can understand from the introduction of the I came to know that you have already had two sessions, two wonderful sessions. One is on material aspects, and other one is the overall perspective of additive. What is the current state and the future perspective of this additive? So my talk will be basically focusing on the design aspects of additive manufacturing, that is well known as design for additive manufacturing technologies. So then why design is so important in additive manufacturing? Is it not a conventional design? Can it be not printable? So those questions will be answered. So you have a specific emphasis on the design in additive manufacturing. Yeah, so because of that reason, as we know that it is an additive in nature, if you see the physics of this additive technology in contrast with the conventional manufacturing processes, then of course we need to tweak the design majority of the times. But you can even print the conventional design also, absolutely. But you may not be able to get the benefits of additive manufacturing once you are not tweaking the design or redesigning or reimagining the design when compared with the traditional designs that are already has been existing or long established. We'll try to emphasize on this. So the presentation outlined quickly introduction to additive manufacturing, and design, again, design is specific to each and every AM process. As we know that AM process physics involved in this is not unique. So as per the ASTM classification, you have 7 AM processes, but all the 7 AM processes, you have a different physics involved. And of course, if that is the case, then your design constraints also different from one process to other process. We'll try to emphasize a quick glance of AM processes with the perspective of design constraints. So that is going to be my idea of keeping it as the AM processes initially. And we'll try to see different design approaches in additive. So that may be right from the scratch or existing design. Just now I'm talking about tweaking or modifying the existing design of the traditional design. So then we'll try to understand the design approaches in additive manufacturing. That is going to be the next topic of my presentation. And as by this time you might have exposed to AM will have
sir, sorry to interrupt, sir. Your screen is not visible. Means only that PPT is not visible, sir. Please.
Is it so?
Yes, sir. PPT is not visible, sir.
1 minute.
No, sir, minimize it, sir.
I will once again.
Sir, try to share entire screen.
Entire screen, sir.
Allow to share screen, allow to share window. There are two options is coming for me here.
Share entire screen, sir. So then PPT will be visible, I think.
Right. Can you please?
Yeah, now it is coming, sir.
Yes, sir. Now it is
now
visible.
It is visible.
Thank
Yes.
you. Thank you.
Yes, please
Thank
continue, sir. Thank you, sir.
Thank you. Yeah, so this is what I'm trying to say. We'll quickly see the introduction part of additive manufacturing and design for additive. Then we need to understand the constraints of each and every AM processes, like which was say standardized by the ASTM into 7 groups, and design approaches maybe say tweaking the existing design or right from the scratch. So then we'll try to understand the design approaches in additive, and AM will have unique benefits like the topology optimized structures. You can very easily you can fabricate, and also bionic designs or bio-inspired designs, or where your designer may be taking the inspiration from the biology or maybe the nature, but how do you get fabricated those kind of bio-inspired designs? So AM is the one among the bunch, we can say. Otherwise, the AM is uh, the only method to give a justification to all your topology optimized structures, bionic designs, which it can be fabricated. So that is the next point of my topic I'm going to cover. And basically, it's a design oriented lecture. So we'll try to understand the design guidelines for part consolidation is another unique advantage, as we mentioned earlier, like topology optimization, bionic design, and also consolidating the parts or reducing the part count in an assembly. So that is also the unique advantage of additive manufacturing. So that we'll try to see some of the design guidelines in part consolidation aspects of AM technology. And the next one is the design guidelines in tooling design. So using the additive manufacturing, you can design a conformal cooling channel for your tooling industry. So India as such, we are very good in tool making industries. No, then you can integrate this AM with the tool industry also. That is another aspect which I'm going to cover. And then design rules for the polymer and metal AM. So you have a different melting temperatures and different physics involved once you process the polymers and once you process the metals, and of course ceramics, composites also now it is possible to fabricate. But there are a slight variation in design consideration while printing polymers or while printing metals. I will try to throw some light on design rules for polymer printing as well as metal printing. And at last, I'm going to give some glimpse of machine learning techniques in AM. But though it is quite early, we can say AM itself is a emerging technology. And once you can integrate the tool like machine learning, artificial intelligence, so it's going to be the double benefit you are going to get it. And that too AM, especially if you talk about metal printing, it's too expensive. So then you can train, you can make a, you can train the model, right? So you can, so that kind of, I will try to cover some of the machine learning techniques that has been adopted in AM. And finally, the build simulation is another challenge, I can say, in AM, but still, then we'll try to see some of the challenges, which includes build simulation in AM. So this is what I'm going to talk maybe next 1 hour or so. So this is the presentation outline. So let us introduce this technology of additive manufacturing technology. So the additive is not a new technology. Probably you might have heard about the word called rapid prototyping during late 80s or early 90s. So that was the term coined during that time. That was the rapid prototyping. Now it has been evolved into a manufacturer's tool. Prototyping is a designer's tool, as we know that, but now it has been matured enough to assist the manufacturer, or rather than we can find a new category of manufacturing processes, that is additive manufacturing has been evolved, right? And also in a common understanding or the terminology of a common layman terminology, even you can say this technology is also called as 3D printing. So whatever you call this technology, the idea starts with the digital data. The input starts with the digital data. Either that digital data comes from a CAD tool or a CAD software, or it may be, sure, sorry, it may be a reverse engineering or a digitized data could also be the start point, or even it could be a medical imaging, like where the CT, MRI, scan data could also be the input for this technology in case of medical applications. So in a nutshell, this is a technology where we need to give an input as a digital data. So that digital data, it may come from engineering domain or medical domain, or even it could be entertainment, or even it could be say archaeology, or it may be entertainment, anything like, but we should get your data in a digital format, and then you can quickly convert it as a physical object. So that is the idea of additive manufacturing technology. So, and then ASTM has standardized this definition. I am not going into that, but the simple idea is take the digital data and then convert that digital data into a physical object, or a physical model, or a physical part, or even it could be assembly, or even it could be say component. So so that is the idea behind this technology. And then why this additive is now it has become a buzzword, though it has been there for the quite 35 years or so, or maybe around 35, 40 years ago, this technology started. But still, we try to understand the key for the industrial fourth industrial revolution is going to be the additive. That's what the survey or the literature is saying, that additive is going to play a major role in Industry 4. As we know that we are migrating from the first industrial revolution, where from the steam power to the electrical power in second industrial revolution, and electronics in third industrial revolution, and in the fourth industrial revolution, where you have autonomous systems, cloud computing, system integration, simulation, Internet of Things, augmented reality, big data, cyber security. But we can find additive is one of the emerging technologies, or the promising technology, or the key technology in Industry 4. So that's where this AM, or additive manufacturing, is going to play a major role in Industry 4. And you try to see now we are in the transition from 4th to 5th industrial revolution. So as we understood, like Industry 4 is more on the automation and efficiency, where the Industry 4 uses the IoT, AI, and the big data, as we discussed. And then cyber physical systems, the focus is on connecting the physical and digital systems to create the smart factories and supply chains. And data-driven decisions, that's what you do in a fourth industrial revolution. Real-time data analytics are used to improve the decision-making and the efficiency. So Industry 5 is all about human-centric, so where the workers are placed at the center of the production and collaborating with the intelligent machines rather than replacing them. So that's what people may worrying about, like say, once the fourth or fifth industrial revolution, then all the jobs will be vanished. But the idea here is the Industry 5 is all about a human-centric and resilience, like where the flexibility and the adaptable manufacturing systems. That's what AM is the technology where you can adopt, or you can customize, you can personalize, right? And quickly you can respond to the changes or any disruption. It can quickly adopt the AM as such. And sustainability, of course, AM, as we are talking about circular economy, and we are talking about the SDGs, that is Sustainable Development Goals. So it is quite inclined towards AM is quite inclined towards the sustainability. So in a brief, so developing the sustainability and product services, that's about the Industry 5, and it will very well fit AM in this scenario. So that's where the Industry 5 is much AM is going to play a major role under this industrial revolutions. And we tried to see the classification of manufacturing systems. So subtractive is the one where we have a lot of concerns like scrap or the complexity or wherever you have design change, quickly adopting or we need to say your subtractive is going to have a lot of constraints, especially if you're talking about your product is much complex. And now we are talking about bionic designs or topology optimized structures. So a subtractive as such, so you have several constraints to meet that demands. So even you try to understand once you change the design from a simple this square or a stepped kind of geometry to a free form like a coffee cup. So then we need to understand several constraints in case of subtractive manufacturing, like your CNC technology or your traditional machining technology. So then, but you need not worry about those constraints once you migrate from the subtractive to the additive. So where it's going to add the material, so your scrap has been a nominal or literally it is zero, or even your complexity is a free of cost here, and a lot of customization. Like we'll try to understand what kind of benefits you are going to get from additive versus subtractive. And of course, you may have a formative process, like we need to make a mold or a die as such, which we need to force the billet or to get the confining the shape of the tool. But that again, how do you make this tool, right? The same story will repeat. But additive, you doesn't require any die, you doesn't require any tool as such. So it's a kind of a new class of manufacturing, we can put it in that way. Yeah, and then you try to understand the decision curve, or the when do you choose your 3D printing or additive manufacturing technology. Of course, wherever you have a highly complex products and relatively a less quantity, that's this guy is right choice. And then whenever you have a medium complexity and medium quantity, of course, the CNC machining going to be the right choice. And complexity is very low and the quantity is very high, like maybe investment costing may be the right choice. And complexity is minimum and the quantity is higher, so probably the injection molding may be the right choice. And these are the steps involved in any typical additive manufacturing process. So by this time you might have understood these 8 steps in any typical additive manufacturing process. Say if you want to make a coffee cup, so then application is to serve the coffee. So in this case, you have a different requirements. But imagine that you are going to make a gas turbine engine part or an aero engine component, but your requirements are totally different. And if you're making some medical device, so in that case, your requirements are totally different. So, okay, whatever may be the application. So we need to start with, say, go with the CAD or a digital data where we have been talking about. And then next you convert that as STL file, that is a de facto standard or a neutral format in AM. And then you transfer this file to a software which is interfaced with the machine. And then you set up a machine setup. It's something like a G code. If you come from the CNC, then something like a G code, but you are not writing any code here, but with a single click, you are able to generate this kind of layers or the cross sections. And then physical realization of this slices will be done in the 5th step, where the layer by layer it is getting fabricated, or it is getting say built inside the machine. And then in the 6th step, we need to remove that part, like say you have some supports, or we need to clean the part, then do that kind of a post-processing next step. Or sometimes we need to increase the mechanical properties, or we need to increase the physical or electrical properties, and so on. So then we can use some kind of post-processing techniques, maybe heat treatment, maybe a surface treatment, or maybe you can use any sort of post-processing method which your application demands, right? Say then, apart from cleaning and apart from removing the supports, even you can integrate your post-processing techniques also here in order to meet the requirement of your application, right? So this is in a nutshell various steps involved in the additive manufacturing process. So then in continuation with our discussion, so the cost versus the number of parts. If you try to understand the conventional manufacturing process, of course, if you want to produce less number of components, but your cost per piece is very high, right? So we need to make a tool. The tooling cost is very high once you are using that tool for producing a less number. But whereas we try to understand what is the break-even point. So if you try to understand the trend for additive technologies, so the cost per unit, whether it is a single part or it is 1,000 parts or million parts, your cost per piece remains same. So then we need to understand or we need to evaluate what could be the break-even point. So then accordingly you can take a call, and this is about the number of parts versus the cost involved or the cost per piece, but you try to introduce the complexity, right? So now, say you have the manufacturing cost versus the complexity. Say, for example, if you have your design is so simple like this, so you may say that this is a 1x complex, but now your product design has been changed to say 5x or 6x complex. Now you try to understand because of this 5x complexity, you try to understand this graph, which because of 5x complexity, your cost is also proportionately increased to 5 times. So in conventional manufacturing process, I am trying to say emphasize here. But if you want to make the same component through additive manufacturing technology, whether this is a 1x complex or whether it is a 5x complex, but your cost remains only 1x. So this is the biggest winner here, why AM is performing good in complexity. So what we can conclude here, your complexity is a free of cost. You are not going any extra money in terms of your complexity. Not only the complexity, you try to understand if you come from injection molding background. So your die, it consists of a conformal cooling channel where your conventional manufacturing system may not be able to make such kind of a conformal channel, but whereas your additive could able to make very easily these conformal cooling channels. So what is a big deal in conformal cooling channel? So your performance of the die has been increased, your die life has been increased, right? So, and then in that way, your efficiency or your functional performance of the system has been increased. So not only the cost benefit, you are going to get the double benefit, even triple benefit, cost also. So again, depends on how much quantity you are looking at. So then obviously you have a triple benefit here, like in terms of cost, in terms of performance. So in terms of complexity these are the three things which your AM is going to give by default, right? So if you compare with the traditional manufacturing methods, and we try to understand the industry, the AM industry, which you can see the consumer products and consumer electronics is the biggest market here, 21.8%, and followed by motor vehicle, that is automobile and automotive together, 18.6, and medical and dental together, 16.4. Aerospace is 10.2, and industrial machines and the business machines were 13.4%. Academic institutions like us, it may be 6.8. Government military 5.2, architecture 3.9, and others maybe 3.6. This is the Wallace statistics. It says about the market share, the AM in various industrial applications. Yeah, then we'll talk about on AM processes. So yeah, I understood like the previous talks were predominantly on the materials and the characteristics of the materials. But I'm not spending much time here. But in a broader sense, so we need to bring the feedstock in any one of these four forms, maybe a powder in a granulated fashion, or a filament in a wire, or a rod, or a sheet, or a liquid. So these are the four broad feedstock forms. And coming to the materials, maybe polymers. Polymers again, thermoset, thermoplastics, amorphous, semi-crystalline. You can make metal alloys, ceramics, composites. So all these four standard engineering class of materials. Apart from the standard engineering materials, functional materials, electronic, shape memory, biological material, maybe a living cell or a stem cell could also be the material, or it may be a food printing, or it may be a 3D printed houses at the construction, or in structures, building the structures, or building the bridges. So you have a diversified materials here, not only restricting to the engineering materials, four class of engineering materials. So you have an additional bunch of materials here. That is the winner here. So anyway, I'm not going to spend much of the time in terms of these AM processes. So the 7 AM processes and feedstocks, as I already mentioned, maybe a liquid, powder, solid. And then AM principle, but it will take longer to explain. But in a nutshell, even it could be a polymerization process or jetting. It may be an inkjet, binder jet, atomizing the powder particles, or melting and solidification, or joining. So all your 7 AM processes may work in a different principles. And of course, your feedstock material and your energy source could be a laser, could be electron beam, could be a plasma, or could be a heat energy or whatever. So you may have a different energy sources, but all your 7 AM processes, you have a specific, say, feedstock form specific. All these are material specific and feedstock specific, energy source specific, right? So yeah, and this is a single step polymer AM processes, which we can understand maybe through a thermal bonding, the fusion. So the biggest thing here, how your layers are getting stick together, right? So it may be through a thermal bonding or maybe a chemical reaction bonding. Basically, I'm talking about the polymer processing. So broadly thermal bonding or maybe a chemical reaction bonding where your AM processes could be catered into say all these polymer processing technologies, maybe as a filament or maybe a melted material, a powder or liquid, or maybe sheet, and even it could be a deposition nozzle through, or it could be a jet, something like your inkjet printer head, or even it could be a powder bed, it could be a print head, could be a vat or a tank, could be a sheet stack. So, and then principles like it could be extrusion process, it could be a jetting process, it could be a fusion, it could be a binding of the powders through the glue or a binder, or it may be a light reactive photopolymerization process in case of your epoxy resins. Basically it works, and fusion of stacking these sheets. So this is about the polymer processing. And talking about the metals, so metals in a single step, probably you may have a 4 predominant processes like DED, material jetting, powder bed fusion, and the sheet lamination. This, why you are saying is a single step means, so within not much of your post processing, so you can make it in a single step. But what about other 3 AM processes? So even you could able to make metal parts with other 3 AM processes, but not in a single step. It could be 2 step or maybe 3 step, maybe making a green part and then followed in a sintering step, and maybe maybe in a furnace treatment. You can do it, but not in a single step. But it may take at least 2 or 3 steps to even process the metals with any one of these 7 AM processes. So with this, yeah, this slide will tell you the story about all 7 AM processes, the principal, process, material, and machine manufacturer. So this is the recent article we published in JOM that is on design for additive manufacturing article recently we published, and somebody is interested, you can refer this review article. I will leave this link or DOI link to the organizers, so you can have, yeah. And I hope like the previous speaker might have talked about a lot of materials, but in a single slide you try to understand your amorphous material, amorphous polymers, predominantly material extrusion process, and maybe polycarbonate through a powder bed fusion. And your thermosets, predominantly you can use 2 AM processes. One is a vat, another one is a material jetting. And you try to understand the semi-crystalline class of polymers. So you have a predominantly powder bed fusion technology for your semi-crystalline polymers. And you try to understand the metals and metal alloys, as we already discussed, 4 AM processes like powder bed, binder jetting, sheet lamination, and DED. These are the 4 technologies predominantly for metals. So with this, the materials and the physics involved in all 7 processes and the material used for all 7 processes. Now, yeah, metal is, you try to understand the metal is going like anything. The metal started in 2000, maybe hardly 26 years back. The metal AM has been evolved, but you right from the 2002 to 2023, now 24. Also, you can see the kind of growth, the exponential growth in metal AM installations. So that is what the Hollers now says. This kind of a statistics which you can see across the globe, how this metal AM is gaining a lot of attention. But this is some of the powder bed directed solid state as we already discussed. So yeah, you have under these three, again with the powder or wire or a foil or a rod or a powder, you may have a laser, electron beam, or it may be a blown powder, or maybe arc-based deposition, maybe a laser-wise deposition, or electron beam deposition. Even it could be ultrasonic additive, or it may be a friction stir additive, or even it could be a cold spray. So and then how do you choose your metal aim process? So that is your precision, or rather than your resolution versus deposition rate. So your powder bed will give a better resolution, but the deposition rates are very low. But if you see the other hand, like arc-based deposition or friction stir additive, so you have a huge deposition rates, but the precision or the accuracy is very low. But you can make only the near net shaped, but your deposition rates are very high. But anyway, we need to compromise, or we need to no. You have a trade-off between your precision and the deposition rates. And powder bed and the electron beam, these are the two major metal which we are talking about. And this is one small video from our lab. This is a powder bed based metal 3D printer or AM machine, where you can see the laser is melting the powder particles, and where your powder particles, even it could be with the order of 25 to 30 micron sized powder particles, and where your laser will be melting the powder particles and you have a loose powder around that. So then again, you have next layer, the roller will spread onto that the previous layer, and your process will go on. This is the typical powder bed based laser energy kind of a source where you can use. And then biomedical and aerospace, these are the two areas where we have a lot of emphasis with the metal AM machines, like maybe a stent, maybe a device, medical device, maybe a implant, maybe a supportive device, maybe a prosthetic, maybe everything is a customized or patient specific is another advantage. And of course, aerospace is the area where we need to have lightweighted structures, or your jet engine components, where it may be made out of so it could be a titanium, or it could be aluminum, it could be a nickel based superalloy, where you can easily process these kind of structures. And you try to understand, you have a lot of nickel based superalloys, right, from the nickel Inconel 625, Inconel 718, Hastelloy, Hines. You have a series of a good number of nickel based superalloys, and you have a copper based alloys, aluminum based alloys, and iron based metal alloys, titanium based, and cobalt based alloys, refractories, quite surprisingly, right from that tungsten to tantalum, so you can be able to process it. And bimetallics also, it is coming in a big way, and metal matrix composites, of course. So these are some of the metals where you can process through this metal AM systems. And you try to understand, anyway, I will come to this design aspects, the process parameters, and how it is getting affected, and how your design is going to tweak. And these are some of the trends in metal AM, like people may be trying to engineer this platelets instead of a powder. That may be the people are trying to do that. And even people are trying to make some kind of metal ceramic interface, or the bonding and high density ceramics. And people are trying in situ process monitoring. That's which you are going to see some AML techniques in that direction, and multi alloy hybrid techniques and increased scale. Now people are even able to print aircraft fuselages also through a DED with a high scaled parts are coming up. And even it could be a shape memory alloy, even it could be support structure. Anyway, we'll try to emphasize some design aspects of this. And non-weldable alloys also people are trying to, and non-destructive evaluation applications. These are some of the trends in metal AM. You can, somebody is looking for some research problem or some area which you want to pick up. These are the areas where in the metal you can do a lot of potential. Yeah, and then we will stick on to our design approaches in additive. So you try to understand the design approaches in additive. So as I already mentioned, you have two broad approaches. One could be designing right from the scratch or using some algorithmic methods. That is a one way. Otherwise, you can redesign based on the existing part. So then why you want to redesign, right? So then the next slide will tell you that story. But anyway, you may be either redesigning the existing part or maybe right from the scratch, you may be designing it. So if you're redesigning it, so you try to understand some of the design aspects like orientation, support structure. So all other process parameters which we need to understand. And it may be a generic DFAM guidelines which you can follow. Or we need to even process specific DFAM guidelines. As I already mentioned, each 7 process will behave differently. So then you may need to adopt some design guidelines as considerations or the constraints which we need to understand that may be specific to a particular process among these 7 AM processes that we need to understand. Or even if you are doing right from the scratch, maybe you may come from the generative design domain, or you maybe come from the topology optimized design. So then you follow the process specific DFAM guidelines and do the design modification, simplification, so and then final part. So this we can have a kind of a design approach in a DFAM. So in continuation with the previous slide, so broadly you can have a 3 redesign or say direct part replacement here. You may be taking that same traditional design here. You try to understand the left most component. So this is which you are trying to replace only the process instead of a CNC or a traditional process. You are trying to use additive to print it. So that is a direct replacement without altering the design. You are you are pass on the conventional design to on a machine, AM machine. So simply you are replacing the process, but not the design. But you're not touching any design aspect here, but simply you're reproducing it. So, but the weight of the component may be 4.6 kg. But like in the second approach called adapt for AM, in the adapt for AM, what I am trying to say, this design philosophy. So you are changing. Of course, the process anyway, you are going to use AM, but you are changing the form also. Instead of this bulk design, I am making a shell. Simply, I am not changing the inlet and outlet. Basically, it's a manifold. So I'm not changing that configuration. Simply, I am making this, the bulk of material into a shell. So just I am changing the form. So here, but because of changing the form, I could able to save 78% weight. So now it is only 1 kg instead of 4.6 kg. So why you are doing it? So next slide will tell you the story why you want to do this adapt for AM in terms of your manufacturability also. Then we will come to that. But still you are not satisfied. You are getting only 78%, but I need to get 91% or 100% benefit. Yes, of course, you can even design for AM is another philosophy where not only the form, not only the process, you are going to change the function also. Why? Because so why only the inlet outlet in this direction? No, you have some manufacturing difficulty in the traditional design, but now you have a lot of design freedom. Now you have changed all the your configuration. So now because of that, so your functionality has been improved. So you have a better functionality now. Anyway, you have changed the form and your fitment also. You see a lot of fasteners here. So now it is a very simple, a modular kind of a design. No, your fitment is very simple, right? So you got the 3 F's advantage. That is the form, fit, and function. So, and not only that, so you reduced 91% weight and also improved the fluid flow and also easier to assembly. Your assembly cost, inspection cost, everything has been reduced, right? So this is the moral of the story. So this slide will tell you the entire design philosophy or why we need to redesign. And in continuation with the previous one, you talk about the manufacturability now, right? So that is the design aspect. Like, so then design is not the goal. So we need to make a physical realization. We need to fabricate it, right? So the same 3 philosophies, that is the bulk design, shell design, and DFAM. So you have a 3 variations of the designs. You try to manufacture the three variations in the design. So the first guy, there's a solid block. It will take a lot of scan time and it will take a lot of build time. So it may be costing you heavily, and your material weight is 7.4 kg, and altogether, so it will become very expensive. Why? Because you have changed only the process, but you didn't change the design. But because of that, we need to pay a lot of money, and then you may be blaming AM is very expensive, right? So means it is not going to give any benefit of AM. But your shell-based block manifold now 191 hours to 36 hours only. So you may be charging. So if you are running a service bureau with a metal AM machine, you may be charging say 750 rupees or 1000 rupees per hour. That is a machine hour rate I'm talking about. So then how much money you have saved once because of your design adapt for AM. So you have reduced a lot of cost here. But further, you have adopted some support or some kind of design for AM guidelines. Anyway, in a while we can see. We'll try to cover as many as we can in a DFAM guidelines. So you adopted all the DFAM guidelines. Now it is only 19 hours. So which we need to understand. Almost you have reduced to one decimal in the cost, in terms of the cost. So you have reduced to 10 times lesser cost that you are talking about. And not only the cost, you may be increasing the functionality, and you are reducing the weight of the component, right? So that is the moral of the story, right? So anyway, this is where your AM, what is the bottom line here? So better always do a redesign in such a way that you will get a lot of cost benefit. The performance, the existing performance versus the modified design performance. If you see, that's what companies like aerospace or automobile, medical, so all these industries, they are behind this technology. So this is a simple. Then why design is so important? So you might have understood the essence of the design in AM, right? So anyway, so you have a lot of design freedom now. Instead of this, always you have a 6 phases in a conventional process. Now your designer have a lot of design freedom. So he has totally changed the design in such a way that your fitment has been simple and your functionality has been increased, right? And your cost has been reduced. So then your designer is not curtailed by his innovation or his freedom, right? So because of AM, that is a conventional versus AM. So that is the biggest. Let me summarize. So you may have the 10 principles or 10 benefits or whatever you say. The manufacturing complexity is free. So whether you make a cylindrical geometry or this bio-inspired geometry or topology optimized structure, whatever you call, but your manufacturing complexity is free. You are not paying any extra amount in terms of the complexity. So your manufacturing complexity is a free of cost. It's coming in AM. And also your variety is free. So you need not worry about writing a different codes in case of a CNC, all 100 components, 100 different geometries. We need to worry about a lot of tooling or a lot of fixers. And then I'm talking about conventional. But here, all these variety is free. It doesn't matter what kind of a geometry you're producing it, right? So then your variety is free. And it doesn't require any assembly at all. Even you can make it more part consolidated. Anyway, we'll elaborate this in the upcoming slides. And then zero lead time. Of course, you doesn't require any supply chain logistics versus your conventional to AM. You need only the digital inventory, right? So it doesn't require any physical inventory. So you need only the digital design inventory, right? So your lead times are absolutely zero. And you have unlimited design space, right? So that's what you're talking about. So designers' imagination or innovation should not be curtailed by the manufacturing capability of the conventional manufacturing process or whatever fabrication technique you're going to use. You have unlimited design space here. So with the AM and zero skill manufacturing. So you are not writing any code at all. So you not worry about what is G code, M code. Basically, your manufacturing skills are zero or minimal, right? And these machines are very compact and now in a desktop based. Now the metals also coming in more compact, not only the polymer based machines. Now you can have a less wastage byproduct. Of course, you are adding the material here and infinite shades of material. So in a conventional manufacturing process, always you can make a single structure components, but you can make a multi-structure, multi-material. That is the biggest advantage, right, here in AM. So you can simultaneously print electronic, non-electronic material. You can simultaneously print a flexible rigid, or you can simultaneously print opaque, transparent, right? So you have a lot of flexibility in terms of material choice and material processing. The material, multi-structures, you can make it. And then you can precisely replicate the physical form into a soft form once you integrate with the, say, digitizing or a reverse engineering technique with the, say, AM, right? So then these are some of the benefits you can talk about. So let me focus on the topology kind of optimization and bionic designs, right? So I think now people are, you talk about the design, the geometric modeling, how it got evolved. We know that you have a 2D drawings, and now then earlier you have a parametric modeling. Now people are migrated into a generative kind of a design, topology optimization, lattice structures, or cellular structures, whatever you call, or biomimicry or biodesigns. So where we can see there will be a grading in the lattice structure. So wherever you need a specific property at a particular region, so you can do a lot of gradation in the lattice structures, right? So that is very much needed for medical or aerospace applications. You have such kind of structures, right? And you can make a lightweighted structures like a topology optimized structures here, or a generative design. So you have several CAD tools to do that designing part, but who is going to manufacture it, right? So then AM is the single solution where you can precisely make or fabricate these kind of structures, right? Yeah, you can see a lot of so a lot of topology optimized bionic designs, maybe in terms of your aerostructures, or even in case of your cabin components, or maybe inside the engine components also. You can have a lot of bionic designs, or lightweighting structures, or internal lattice structures, where you can companies like Airbus, Boeing, so they're adopting this kind of a technology. And also you can do a monolithic thrust chamber. This is one very well-known case study in aerospace application, where you can make your combustion fuel injection area and thrust chamber as a single integral part without any assembly, right? So, and then you have a lattice structure here where it will improve the cooling efficiency and more into a lightweighted structure. And traditionally they used to make with the CNC. That is very difficult to process the nickel-based supralloy like Inconel 718. But now you can very easily make it through this AM in a monolithic structures. And even you can see these designs, bionic designs, are heat exchangers. So then lung inspired heat exchanger, the function of the lung. The same thing can be mimicked here in the heat exchanger, where your cooling efficiency has been increased. And even you can print in copper. Earlier, you don't have any choice of printing with the copper in AM, but now you have a copper could also be the 3D printable material. So with some limited AM technologies can print this. So you have the best material, and the best design in the universe. That is bionic design, of course, and the best material in the universe, maybe copper in terms of your heat exchanger, if you're talking about. So you have the best in the business in terms of material, in terms of design. So then that is what, like, where your heat exchangers and your AM is going to play a major role. And also your personalization of shoe soles, like which you have some, you can personalize your, so each person is unique in his weight or dynamics, the all that mechanics part, but you can very well personalize as for the patient requirement. That's what people like Adidas or Nike, they are using this kind of technology to print a personalized shoe soles. And in the fashion industry also, people are using this for personalization of these. And then most importantly, I'm sure maybe the other speakers may be talking about more into a biomedical applications. But biomedical is the area where you are intentionally making the porous structure, or you are trying to mimic the bone structure or the human anatomy of a particular patient or a patient specific implants, which we need to make it. And this is the guy, that's what companies like Anatomics, Zimmer, Stryker, all these companies are behind this technology, where you can do a lot of maybe a chest implant, maybe a spinal wedge or whatever it is, or it may be orthopedic cast, and you can make combinedly the cancerous bone and the cortical bone in a single setup without gluing it or without assembling it. So that is the biggest advantage here, which you can. I'm not going to touch up medical here, but then let me focus on the next topic. That is a part consolidation. So part consolidation. So you try to understand this design. It has a 19 components, and you have a lot of fasteners here. But once you consolidate, it's only 4 components. Anyway, sensors are not replaced, but all these mechanical fasteners, and you have a kind of a clip kind of a design where it has reduced your 19 components into 4 components. So which you can say make it in a single go. And even we can see okay. So even you can make, you try to understand this component. You have 48 fasteners here altogether, but 48 fasteners with 5 components. So you try to understand 1, 2, 3, 4, 5. But why we need to have these 5 components, and then why we need to assemble it through a 48 fasteners? Maybe that may be the limitation in manufacturing method that you have adopted. But if you have a manufacturing system which can make any free form, any kind of any geometric form or any free form that you can make it in a single setup, why not? You can make it in a single setup, right? In single go. That's what your AM is going to play a major role for part consolidation. This part consolidation concept, GE has explored a lot, which we can see 20 parts. Now they made a single part. This is a LEAP engine in a nozzle they used in a gas turbine or in jet air engine. They are using its GE. And the benefits: 95% inventory reduction, 25% cost reduction, 5 times durable, and 30% cost efficient. And also you can see several part consolidation, maybe from a Boeing, say 700 series, or even GE 9X series engines. So they are saying 300 parts has been consolidated, and it's the most fuel efficient engine in its class. And you can see 100 parts has been consolidated in a single part. So the traditional way of making is a brazing and EDM, but now it is a 3D printed laser fusion, and 95% weight reduction, 20% reduction in cost, and 75% in the non-recurring cost elimination. So these benefits one can understand. And this 300 parts has been consolidated in single unit. This is a diffuser component, and with weight reduction is almost like 10 lbs. So that is what the weight reduction has been happened. So even 1 gram saving is a good enough to payload reduction and further the fuel efficiency, right? So that is what your aero industry, the AM is driving here with that. And then even GE Catalyst series of engines, 1/3 engine parts they are trying to print through AM, and so less supply chain and less assembly, less maintenance, and more than 100 lb means more than 50 kg reduction in this Catalyst series of engine. That's what GE is quoting. And also these qualifications from FAA or other regulators like Indian regulator like Semilac, or foreign regulator maybe FAA, but they are quite quick to qualify or to certify these kind of components. That's what it's happening. And you can see some of the part consolidated things here, from the traditional design to the consolidated design, and fabricated, of course, through a metal AM system, and which we can see there are 20 parts. Now it's only single part, and we can see some 12 parts. Now it may be very few parts here, like maybe you can understand the part consolidation. And the next one is a tooling industry, right? Where conformal cooling channel, like unless you have straight channels through a conventional tool making industry, but now you have a conformal cooling channel, which your coolant will be confining to the shape of the component, so where you can extract the heat very effectively, right? That's what your conformal cooling channel. So why this conformal cooling channel? Your cooling stage, it takes 60 to 70% of your cycle time. So that's what you are targeting, where your conformal cooling channel is the guy who can do a lot of reduction in this area, and also your of course these are other times which you can understand. So you can have this cooling channel designs like which we need to understand traditional cooling channel versus conformal channel, where you can see a lot of here you can see the shrinkage or how it got accumulated here with a non extracting the heat in a more non-uniform direction here. But where you can understand here, you have internal stresses are minimal, and you have your errors has been minimized, right? So, and then the shrinkage and the distortion has been minimized with this. Not only this, and the the tool life has been increased because of this conformal cooling channels. So you can see several design strategies, maybe the pattern, how your the coolant will flow. That is like the pattern, maybe a zigzag, parallel, spiral, and then even the cross section of your cooling channel. You have a standard. Rather than you have some guidelines to be followed, so in order to use this more effectively. So then you can see some literature, people are trying with different cross sections and different patterns to in order to improve the cooling efficiency of the tool, right? So yeah, you can see like how your cooling channels has been integral part of your tool. So you're not design separately, assemble it, but your based on the feature, your cooling channel, conformal cooling channel has been designed, and it has been printed in a single attempt, maybe through a powder bed, maybe a DED, whatever, a metal tool steel you can very well use here as one of the printing materials. And then we'll focus on the polymer design. Yeah, the orientation is going to play a major role. You cannot get the same property, the unidirectional property. Most of the time, it is anisotropic nature, AM. Why? Because you are adding the material. But adding the material in which direction, it will judge your mechanical property, or it will judge your the strength or spring effect here in case. Then you have a lot of freedom here to fabricate any orientation, but which one works for you? So again, we need to understand the application or the functionality of each and every feature, and what is the critical feature in your component or in your a product, right? So based on that, whether you need to fix this orientation to fabricate, or you need to fix. So if you fix this, yeah, obviously this is very weaker clip, almost certainly it will break. But if you could able to make in this orientation, yes, you do compromise the clipping, spring action and your strong hook. But like if you have another option of fabrication, this orientation, so it has the best spring, but still your hook is weak, right? So what is the moral of the story? Yeah, then we need to understand the application, or we need to understand the functionality, the critical feature. Based on that, we need to select your orientation. That is where you can minimize some extent this anisotropic nature, and of course, which we need to follow that kind of guidelines to fix the orientation. And wall thickness could be a light weight consumer products could be 0.6 to 2.5, and heavy duty it may be 3 to 5 mm. And then say don't use this kind of say better always don't lie in this orientation. Why? Because you have a huge residual stresses build up at the same in the single layer. But instead of making this orientation, you make some 10-degree where your residual stresses has been accumulated not in a single layer, maybe 1, 2, 3, 4, 5, some 10 number of layers, some 20 number of layers. Again, depends on the layer thickness that you're using it. So then you can consider all these design say constraints rather than guidelines to fix up your orientation, wall thickness or whatever. And then these support structures that your overhang angle is going to play a major role. Then once you start using this technology, then you can very well say control this kind of angles that is where you can do a lot of minimization of this say support material. For example, you take 60°, it doesn't require any support, but this is a 40°, it requires a support. And you have a bridge kind of feature, we need to provide the supports here. And you have a overhangs here, we need to give the supports. And the orientation matters a lot. You can see the green color one is a support. So what is the amount of material that is going to consume in this orientation is different from this, from this. So use some design for aim guidelines where you have a minimal support structure here. Or sometimes we need to tweak the design some extent, even you can minimize your support structure. So all these which we need to follow these guidelines or the considerations while fixing your design and so on, right? So, and of course, you have some guidelines to be followed in this direction. And then the thickness is another matter. If it is 2 mm thick, your all 0.5 mm hole or slot can be realized, and even 2 mm, 0.5 to 2 mm. But if you increase the layer, the thickness of the wall, it may be 4 mm, but this feature is missing, right? So we need to understand these constraints. So then based on that, we need to redesign these holes, or then we need to come out with a kind of the guidelines or which it should be followed. And rips is another area where you can increase the strength rather than, and then your other one is so you have some kind of superficial kind of material where you can remove inside the say especially for a kind of vat system or a powder bed system, your loose powder or the liquid can be entrapped. So then how do you avoid such kind of a thing to provide a drain hole and taking out that material? And then metal, yes, of course, metal we have a bit challenging than the polymer. Why? Because you have high melting temperatures, and so then we try to understand some parameters like scan space or layer thickness or scan speed, and your energy absorbed or energy reflected, energy scattered. So you have none of the laser is efficient more than 70%, even it may be 20%, 30% efficient, these lasers. But nowadays you may have some kind of fiber lasers where again the efficiency may be less. But anyway, so you have some lack of fusion, pores, cracks. Then we need to understand, and then how do you minimize this? Maybe by adjusting some process parameters and some which we need to understand. Maybe you can play with some of the parameters, or you can even change this scanning strategies in order to distribute your residual stresses. Basically, that is a major challenge which we need to handle. And energy density, maybe once you model this kind of then we need to understand the energy density. It should not be too much less and should not be too much high. Then we need to optimize this energy density is the function of laser power, your scan speed, and your hatch space and your layer thickness. So this is the kind of relation that we need to understand. And large horizontal surfaces, always you try to minimize that kind of stuff. And as I already mentioned, the overhang angle that dictates a lot in terms of your these supports. And also where we need to understand these overhangs, what is the minimum the overhang angle or the thickness which we need to. And these bridges, what could be the bridge? Maybe 1 mm, 2 mm, it's fine, but 3, 4, 5. Then we need to take some kind of a design guidelines to adapt in order to realize all these features very well. Otherwise, you maybe end up with a bad component. And residual stresses, as I already mentioned, so it may detach the support to the model, and also a lot of cracks, internal cracks. Then one way of doing it is you change the scan patterns, like you can optimize these patterns in order to reduce these residual stresses. And also the thickness is another area where you try to maintain the uniform thickness across the entire structure rather than abrupt changes in the thickness. And of course, the stress concentration and the uniform thickness across the walls. And the horizontal holes, there is another challenge in metal aim, especially if you try to understand maybe up to 2 mm, 4 mm. 6 mm fine, but once 8 mm, 10 mm, 12 mm, 14 mm, 16 mm, 18 mm, 20 mm, without structure, without support structure, you cannot realize this kind of. Then what is the solution? Maybe you can use some kind of. So if it is more than 8 mm, either you redesign it to a elliptical or a teardrop or a diamond kind of a thing. There are some guidelines which we need to. And then some positioning of this also matters a lot. You take a typical powder bed, the roller, how it is touching your part, like the contact area with the roller to the part, that matters a lot. Then which we need to understand, we need to give a less force, less stress or the less pressure to the part with the roller. I'm talking about the powder bed paste. And we need to follow some guidelines. The part positioning, don't put in line, but you maintain some gap like this, right? Again, the same logic, which you should not give a much pressure roller to the part. And also sometimes it will damage the part, which you need to understand some bad component, or which it has been, your roller has been, hit the part here, the features here. So why? Because you didn't follow that guidelines. Then we need to follow those, and the height is also matter. Then which one we need to keep it. So all these part positioning guidelines which we need to follow. And of course, each process will have its own constraints. So because running short of time, I might not be able to explain all this, but anyway, I'm sharing this PPT. Each process will have some constraint about the wall thickness in all AIM processes, and support also, and the embossing, engraving textures, holes, and also clearances, pin diameters, escape holes, and the holes with ideally, which we already discussed, like teardrop, fillets. Yes, you can always have some kind of modification, preferably like this, right? So this is the ideal. So which we need to understand. And there are some design for AM people or developing some kind of, even in the portals, like, so you have, this is one from the Purdue University. So they made some kind of design for AM evaluation. You can import your design, and then it will tell you the score. So based on the score, whether we need to redesign it, or we need to consider the redesign, or we moderately or badly needed to change our manufacturability aspects. So then you can very well. And let me come to the last part of my presentation, machine learning techniques. So of course, I'm not an expert in using these tools, but let me give an insight of these ML tools in AM. But still, it is early. I can say AM itself is emerging in terms of its material, in terms of its applications, and so on. But here.
Sir, I think you are muted, sir. Sir, you are muted. No, okay.
Hello?
Now can hear. Earlier it was
No, actually, my AirPods, it got right. Now, are you able to hear me?
Yes, sir.
Now audible,
Yes,
sir. You are audible.
yes, sir.
Yeah. No, I am removing my AirPods. I may be using the speakers. Now, is it okay?
Okay, sir, no problem.
Right. Thank you. Yeah, and then you can do a lot of microstructural modifications that will enhance the properties, tensile, hardness, toughness, density, and where you can do a lot of grain refinement, surface porosity, kind of imperfections in the planes. In microstructural things you can control very well. So you just the idea of any ML. So we need to create a closed loop controller, right? That's what where your closed loop controller and defects can detect, and automatically it will be adjusted. Your parameters is automatically adjusted. So as for your real time you have a sensors to capture, right? So then, but still, I can say this is an initial stage, but lot has to be matured in this direction. But there is an idea like where you can do a lot of integration of machine learning kind of a tools here to integrate your am further to enhance your properties and microstructure control, and you have a closed loop control here. That is the biggest advantage of your any trained data in case of your machine learning techniques. So you try to understand maybe machine learning, your supervised learning can be regression techniques for process parameter optimization, part property prediction, a geometrical deviation control, and closed loop controller. And classification techniques can be used for detection or quality assessment, quality prediction, and geometric deviation control. And clustering algorithms can be used for geometrical deviation, cost estimation, and you have a data pre-processing kind of applications. And I have listed here all 7 AM process. Basically, this is one of the review paper I took. And all these 7 AM processes, various ML techniques used to enhance what kind of property, maybe optimizing the laser power or optimizing the or predicting the quality or monitoring the DED thermal images or in situ capturing of this, or the filament temperature, nozzle temperature optimization. So you have a lot of tools in the literature available. People are integrating maybe DNN, ANN, and GPR and so on with the even all the 7 AM processes, which it has been listed here. Yeah, in a broad sense, design for AM, as we already discussed. So you have a lot of scope to material design, topology design here to integrate your machine learning technique here. And also AM production like manufacturing planning, quality control, data security. That is another challenge which we need to address here. And AM processes like your characterization of the powder spreading in case of a powder bed system, or it may be a DED with the powder, or process optimization, in-process defect monitoring can also be trained here for your AM process optimization. And these are geometric design and the process parameter configuration and in situ kind of detection. You have how these AM technologies and what purpose they are using it and what parameters they are optimizing it, and the algorithms or the toolboxes people are using for the kind of a topology optimization or a genetic algorithms to integrate, or machine learning methods to have, like as we discussed, like ANN or CNN are kind of a techniques or which it has been integrated here for AM process optimization with the ML technique, or as in continuation with the quality control, microstructure optimization, material formation. That is the biggest benefit here to design your own alloy, right? So that is the biggest and process parameters and design optimization, like as we discussed, like it could be a bio-inspired design or topology optimized, or maybe a lattice design. So that is in case of bioprinting, bioelectronics, construction, drug, electronic, food industry. Quality control, people has already used this kind of ML techniques to integrate to use it for a quality control purpose of AM. The consistency is the biggest challenge still in AM, to make these parts how best consistently you can produce the quality. That is the biggest challenge still. It's an open challenge in AM. And that's what, like, in process monitoring with ML will help you out to bridge that gap some extent for monitoring the melt pool shape or thermal imaging or melt pool intensity. All that you can do a real time in process monitoring, so where you can find some lack of fusion or keyhole porosities. Then how you can have a closed loop a system here to minimize this by automatically adjusting the process parameters. That is what where people has to, or like people I can say, like it may be in the initial stage, but which we need to wait for that time to mature this techniques to integrate it in AM. Yeah, you can have several areas where you can do a lot of process optimization, material design aspects, and data extraction and optimization, right? And then in design aspects where your topology optimized bumper or a wheel or suspension arm or a driver shaft and so on. and these are some of the topology optimized structures where you can integrate your ML here to train this kind of a data set, maybe from the literature, from the real time collecting the data from the machine, right? So you can create a huge data set here to train this, right? So to optimize this kind of a designs. And let me come to the conclusion part. And of course, the build simulation is still people may be using a multi-physics, multi-scale modeling to simulate this kind of compensating the distortions, compensating the residual stress, or minimizing the residual stresses, and distortion compensations, and support structures, and recoder damage. Or so, though you have softwares which are specific to the proprietary domain. Say we have a machine here, and we may be using a 3D export. That is a proprietary software from the 3D systems, and it may be some other software which is specific to that machine, maybe work, but still it is not into the open source kind of thing. These simulations, I'm talking about the metal aspect, but polymer aspect, you may have a lot of open source simulation kind of packages, but still this should be further. No, you can even integrate this into ML approach, as I already mentioned. So to further enhance this kind of quality checks or thermal distortions, how you can train a model here, right, to compensate any deviations coming from the CAD to the final fabricated part. Yeah, then in a nutshell, ML approach to understand the process parameter configurations, the controllable parameters. So at least you may have around 200 plus parameters to I'm talking about the powder bed based metal printer. So then how do you optimize that parameters, and then all that you can create a model here, right? So, and then you can train the data, and then you can do integrate this, right? And simulation softwares, as already mentioned, you have some proprietary machine specific technology specific AM simulation softwares like additive print or 3D export, or it may be maybe like additive manufacturing, DZMAT, and NetFab. It is open source, but still but the limited features, or maybe it may not be say that kind of so what you call the proof of concept for various AM processes. And you may have sim center from Siemens. You have some though you have proprietary kind of a software for simulation stuff. And fabrication challenges, as already mentioned here, the ASTM or ISO standards are very less. This AM journey started in late 80s or early 90s, but ASTM has formed F42 committee in 2009 only. So hardly you can have around less than 75 published or developed ASTM ISO standards in terms of your design aspects, or in terms of your feedstock aspects, or in terms of your say characterization of the powders, or characterization of your wires, or even your so design for AM standards, but these are very few. So as we already know that, so at least you have several process parameters. It may be around 250 plus process parameters, which it is going to affect your consistency of your build quality. This fishbone diagram will tell you the story right from the operator to the pre-processing to the processing to the post-processing to the part to the AM system to the material characterization. The metallurgical properties are handling rheological properties. So it is not that much easy to optimize, rather than, again, if you change the material, so your entire physics will vary, right? So your melting point is different, and the residual stresses are more in. No, you cannot generalize saying that. So you have optimized this set of parameters for this material. It may not work out for some other material, or if you change the composition of your metal alloy, so again you need to work out for your optimum set of process parameters. So yeah, let me summarize my talk. So we started with the introduction to additive manufacturing and some AM processes, like how the design aspects will bring into that AM processes, the design constraints or the guidelines to be followed. It will be varying from one process to other process, and within this process, one material to other material. And design approaches, as we discussed, maybe right from the scratch or existing design changing, or maybe direct, or maybe adaptive, or maybe design for AM approaches. And topology optimization and bionic designs also we have discussed, and design guidelines for part consolidation, and design guidelines for AM tooling design, and some design aspects. So I might have given some glimpse of polymer design guidelines and metal design guidelines, and machine learning techniques, how it can be integrated for the AM for the quality or maybe characterization, maybe enhancing the properties, and making a closed loop controller to enhance this kind of optimizing the same processes, and build simulation and challenges. This is what we have discussed. And these are some of the facilities we have. We have a 3D systems DMP flux metal AM machine of powder bed technology, which can print in steel, which can print in nickel based supralloy, which can print in titanium, which can print in cobalt chrome, which can print in aluminum alloys. So we can try with other materials also. And then we have a project 3D systems, a material jetting system. Basically, it works even with the 16 micron layer thickness also. It will go up to that resolution. And we have a Stratasys make machines. And then we have a desktop machines. Basically, we use it for the academic and the research purpose. And we have AM softwares like Mimix, Magix, Thematic, and simulation software like 3D Expert that will work for this metal powder bed based 3D systems machine. So these are some of the AM facilities. Yeah. So that's all from my side. If there are any questions or any clarifications, let me know.
Sir, what is 4 refers to in industry 4?
4?
Sir, what is 4 refers to in industry 4? Like you mentioned industry 5, the skilled workers are like something you told. So what 4 refers to in industry 4?
No, this is like, say, you have a first industrial revolution that is from 1780s. So this is basically the time scale. So you have the first industry revolution 1780s to 1860, and second industrial revolution is 1870 to 1960, and third industrial revolution is 1970 to 2010, and the fourth is after 2010 to 20, but now it is a 5. So that refers to the time scale only, the where you can understand from 4 to 5, hardly it is taking only 5 to 10 years to migrate or to evolve one industrial revolution to the next industrial revolution, like 4 to 5. But whereas you can see a lot of 100 years difference here from 1 to 2 or 2 to 3 and so on. So basically it's a time where from 4 to 5, hardly it is taking 10 years of time to evolve new technologies, maybe in terms of sustainability. Once you are talking about industry 5 is all about human centricity, resilience, and sustainability. So yeah, it's basically the time scale. So from one industrial revolution to the other industrial revolution. So it started with 1, and now we are in the 5th industrial revolution. Yeah.
Okay, thank you, sir.
If with any other questions, participant, please unmute and share your questions with the speaker. Participant, please unmute and ask the questions with any questions.
Sir, good evening. This is Jayesh Dange. Good evening. I would like to ask that this additive manufacturing concept takes take into account the complexity in shape and the contours as such of the product design. But as far as material complexity is concerned, how does it you feel that it is addressing nowadays? Material complexity.
Can you please elaborate material complexity in terms of maybe processing, you want to say?
No, no, the type of material that is used to manufacture, because we may require different material properties along different directions. Does it have that, does it reach to that level of advancement to take into account the complexity in materials that needs to be taken into account? Has it reached to that level, or it is in process, or
Um,
what? Can you please?
yeah. Honestly, I'm not a material scientist, but as a general observation, over the period of time, this technology, how it got evolved, but definitely, which we can understand, this technology started with the polymer. Polymer is the one where you can, no, relatively talk about the metal or the ceramic or the composite. Now people able to process even composites and the ceramics apart from the metals. But this technology started with the polymers earlier, with the during late 80s or early 90s. So, but we never thought that it is going to address the metal printing or ceramic printing or the composite printing. Yes, it has been, but still there are several challenges. I can agree where which it should be further addressed in terms of your residual stresses that has been built and at the interstitials. Yeah, I definitely, we can see a lot of no maturity levels year by year. Maybe the metal printing started in 2000, maybe last 25 years. Yes, you can see a lot of maturity in terms of material processing and the quality or the mechanical properties that you can achieve. So I can give literature saying that you can get properties of these additively manufactured parts which are on par with the casting, and which are inferior than a wrought or a forged component. Yeah, it will fit in between casted and the forged component in terms of your mechanical property you are talking about. So definitely it will fit between casted and the forged one. That's not my words. The literature is saying that it's going to be, sometimes it may be better than the casting in some aspects. If you try to refer some literature, especially for the DED technology, or even for that matter powder bed metal components, so it may be on par with the casting, it may be a bit inferior than the forged components. You can put it, you can compare in that way. Yeah.
Thank you, sir. Thank you very much for the detailed elaboration. Sir, can you give some little idea that what would be the approx cost for basic printer in metal powder as such? Approx.
Yeah. So I can say as of now, make in India machines also coming. I can give a couple of companies where they're doing great in terms of powder bed as well as the DED systems. Yeah, so now the cost, typically you can say the majority of the cost goes towards a laser. So say laser cost itself maybe around 50% or 60% of the cost of the machine. So I can say as of now, with 100 by 100 by 100 not less than 60 lakhs or 50 to 60 lakhs, maybe the typical cost. As I already mentioned, maybe the cost of the laser, if you use IPG laser, but it's a more reliable laser, but the cost may be a bit expensive. Yeah, definitely 50 to 60 lakhs, maybe you can get maybe around 100 by 100 by 100, 50 lakhs, maybe around. Yeah, you can see the cost maybe drastically reducing it. We purchased around 1 crore, that is 2020. Yeah, I can say maybe around 25 to 30% cost reduction happened last 4 to 5 years. Yes.
That's great, sir. Thank you. Thank you.
Thank you very much, sir. Actually, there are several more questions, sir, in the chat box. If you can refer to and quickly address few of the questions.
Yeah, if I have a
Uh,
time,
yeah.
definitely. Yeah, if
Yeah,
I
yeah.
have a time.
Actually, our next speaker is in line already onboarded. So
Ah,
quickly, if you can refer, and then otherwise, I will mention all those questions separately in a mail and also with the participant detail, so you can answer those through the mail.
okay, okay, okay. No, I think I might have given elaborate discussion on some of the questions where it has been raised. But some general questions also I can find.
Well, sir, otherwise, I will mail you all those
Yeah, please,
questions
please.
with the email of the participants so you can discuss with them. Yeah.
Yes, yes.
Yeah, so thank you very much, sir. Thank you for the insights yeah, on the design for additive manufacturing. It was wonderful to listen to you and also the different applications and challenges and also the journey of the additive manufacturing. It was wonderful for all the participants. Thank you, sir.
Thank you.
Thank you very
Thank
much.
you. Thank you, Kiranji. Thank you for the opportunity. Thank you.
Yes, yes, thank you.
Bye-bye. Bye-bye.
Dr. Suhas, you are there on board? Dr. Suhas Deshmukh? Dr. Suhas? I think Suhas is not joining. Okay, so slight change in the schedule. Unfortunately, we could not have for this particular session Dr. Jeshu. He has urgent assignment came in the afternoon only. So he has requested his co-worker, Dr. Jeva Khan from the Imtech Germany, and she will be delivering the activities which she has done with Professor Jeshu from MTech Germany. So I request Dr. Zeba Khan to proceed over this particular session. Over to you, Dr. Zeba.
Hello, everyone. Thank you for the introduction. I will quickly share my screen and then begin with the presentation. Can you see my presentation slide?
Yes, Zeba, it's visible. You can go ahead.
Wonderful. Thank you. So I will be presenting not from the side of IMTech, which is associated with the University of Freiburg, but from the side of Handschickert. It's a research institute of which I will give you a bit of introduction. So Handschickert Institute is based in 4 locations, now 3 in Stuttgart, Freiburg, and Villingen-Schwenningen. These are in the south part of the Germany. This particular map that you see is of Baden-Württemberg. This is in the southwest, so bordering with Switzerland and France. As of 2023, this institute comprises of 278 employees, and they are a member of the State Alliance for Research. So this particular chair was developed with the help of these professors who are part of also University of Freiburg, University of Ulm, and University of Stuttgart. The main sectors that the Handschickert Institute works in is in research, for exploring the future, as mentioned here, for engineering, manufacturing, and also for new startups and spin-offs. Coming to specific our group and our division, what we work in here is the research and engineering on molten metal printing through the Starjet technology. So this is part of additive manufacturing of electronics. With the help of Starjet, we want to take the additive manufacturing of electronics in a different direction, which I will present to you now. So the reason is that we have seen so far how the PCBs are manufactured, as you see in this image, with multiple number of steps, multiple processes, which are chemically exhausting and also time exhausting. And this is not an approach for sustainable or green additive manufacturing. which we aim for. The second one that you see is a quick prototyping, because with additive manufacturing, you can create a CAD program and immediately relay it to the machine, and you have your prototype there. Also, one of the very good advantages for this technology is that you're able to fabricate complex structures. So something like this, which you would not would have much more trouble because of the negative parts, the inside hollow parts, etc. So these are some of the advantages which can be coupled for even electronics in form of 3D electronics. One more advantage is the reduction in waste. As the name suggests, it is additive manufacturing. So compared to the subtractive fundamental CNC manufacturing, it has potential for reduction in the waste. The second one would be in this direction, customization and personalization. This here in the image, you see a small blood pressure sensor for produced from Hanschig Stuttgart. This is an ear wearable item which can analyze the blood pressure in a person, and this is customized to the shape of a person's ear. So this is something which is also easily possible with additive manufacturing as compared to printing the object and then applying some 2D printed circuit boards around it. And finally, one of the most important advantages is the smaller footprint that this technology presents. With this motivation, I would like to introduce you to the current research and their limitations in the additive manufacturing of 3D electronics. I'm pretty sure many of you must be aware of one of the leading companies in this direction, which is Nano Dimensions. It fabricates printed circuit boards, as you see here. This particular printed circuit board was printed with the help of dielectric ink and conductive ink. So the dielectric is the yellow or the orange ink, and the conductive is the silver inks that you see here. They have also showcased how neatly they can assemble some capacitors, resistors, some ICs, etc. Another example here for the current research is the main component of this printed circuit board, which is the conductive ink, which in real form is something like this. So it's a nanoparticle-based solution, in which you remove the solution and you're left with the nanoparticles, and upon pressure or heat, this can come together and create conductive tracks. However, they come with some achievements and limitations both. The achievements that the current technologies show are that you can have these conductive traces as shown on the board here possible. You can have the components already possible, and you can have multi-layer circuits. So this circuit that you see is a multi-layer circuit because you have some vias that you can see at these points. And even though the current state-of-the-art research in additive manufacturing of electronics presents such nice achievements, they come with certain limitations. So these limitations would be suboptimal conductance of the ink. And this is because, as I show here in the photo, this ink is because of the nanoparticles, and these are not able to fuse to the level that we would want to get the good conductance that the material inherently presents. Because we are limited by the dielectric substrate, these polymers cannot go to the temperature that the conductive inks usually require for sintering. Nevertheless, to even bring it to the conductive state, we need long hours of sintering processes, and this is another limitation from these. Moreover, to be able to adhere these inks onto the substrate such that they're able to pass some reliability tests for being consumer electronics or any kind of application, the substrate also needs to undergo surface treatments, and thereby these two things could come together and have a good adhesion between them. And finally, even though it is an additive manufacturing technology, it still comes with multiple setups, and this limits the design freedom. If you have to move the object and you have to change it into different machines, this means that you're inherently reducing the design freedom, which could have been possible by additive manufacturing. For this particular idea, we go for our Starjet technology here at Hanshikad. This Starjet technology is an innovative technology patented at Hanshikad and University of Freiburg. This particular technology is able to print digital non-contact printing of molten metals. That means the metal in its most raw form is used in the reservoir, and we're able to eject tiny molten droplets to create, in this case of additive manufacturing of electronics, conductive tracks. How this actually works, this particular technology, is that you have a reservoir of metal, as you see in the green, around which you have the resistive heater that heats up the substance inside. So this resistive heater is shown in the yellow color. And the blue is the substance, the raw material, which is nothing but metal. And finally, to be able to dispense this metal in the form of droplets, we need some kind of actuation. And in this particular case, we use pneumatic for our actuation. So we provide from the top tube that you see here actuation gas. This gas pushes the metal, and then the key component of the Starjet technology, on which the name is based, is the Starjet star-shaped chip. So this chip you can see in green color. This is attached to the outlet tube of this reservoir, and this particular chip, because of its microfluidics properties, is able to eject single droplets out of it, as you see in this enhanced image. To add to this functioning of the Starjet, we also provide these channels through which we can have a gas which is given an inlet through this particular pipe that you see on the side. And this also enhances or helps in creating not only the droplets in center, so that it maintains the directional stability of the droplets, but also it prevents this molten metal from quick oxidation, because if molten metal would come into contact with oxygen, you would have a very thin layer of oxide created immediately on top of it, and this then creeps into the inside of the material, ruining the material's conductivity. So in order to prevent such an act, we also have this nitrogen gas flow from the side of the Starjet printed. All in all, we have good amount of material profile that we can print, and also the types of printing that we can do. For example, we can have droplet printing, or we can have jet printing. The materials that we can also use in this case is one of our most used material is the SAC 305, which is a narrow edge compliant material used mostly for the electronics industry for soldering purposes. Another material we also have is the bismuth material, which is a low melting point solder, which we also print for other applications. And now we also have some high melting point materials. And if you see here in this chart, even though there are people who are able to print copper in terms of conductive inks, like I mentioned earlier, it is difficult to sinter it to the temperature that you can get the actual conductivity of the material or the conductance of the material. And there is where we have the advantage, because we are printing bulk metal, and despite this conductivity difference, we're able to achieve the conductance needed for the tracks. And for this purpose, we developed a one platform hybrid printing technology to create fully embedded 3D electronics. This includes conductive traces with resistance less than the state-of-the-art nanoparticle-based ink traces, flexibility and polymer substrate selection, as you see on the right bottom here, layer by layer 3D printing of metal and polymer. So we are able to print substrates, we are able to print conductive tracks shown in yellow here. We're able to also print additive manufacturing of vertical interconnecting vias. And overall, this process does not require any pre or post processing. As I mentioned previously, the substrates for most of the dielectric based inks need some kind of surface treatment to ensure that the inks are able to adhere to the surface substrate. And this is something we are able to eliminate with the help of our polymer portfolios. And we also do not need any post-processing of the printed parts. That means we do not need any sintering since our metal is in the bulk form. And finally, we have application-oriented characterizations that we have developed here. That means we have done reliability tests, we have done some industrial scale thermal shock tests, etc. To give you a brief overview of the concept of the hybrid metal printing, this methodology consists of an FFF printed. I'm pretty sure you've had a number of lectures already before where the FFF technology was elaborated. But just in a nutshell, FFF printed works with the help of extrusion-based principle. That means you have filament in the form of a spool, and this filament is passed through the heated nozzle and extruded as filaments and deposited layer by layer to create the substrate. Now, the concept behind hybrid printing is that we want to print two different technologies on the same machine without moving the object. So we have the FFF printed and the Starjet printed next to each other, and our concept was to print them sequentially one after another by depositing molten metal micro droplets next to each other and create traces. For this technology, we created a model which was based on a Snapmaker A350 FFF desktop printing platform. We did modification into the platform to include our printing module on one axis, to have a monitoring camera, to have a smaller print bed which would accommodate to our printing needs. We have the linear module axis here and a stroboscopic setup. I will explain later in detail what the stroboscopic setup is for, because it's one of the crucial elements to ensure the molten metal printing from our Starjet printer. So this particular printer was developed here at Hanchikut. This developed printer from the model itself, as you've seen earlier, now successfully has an FFF module. It has the top view camera for future assessments of failure modes of prints, which can be done with the help of some AI assistants. The Starjet printed, which prints the metal as shown. The side view camera for online monitoring or live assessment of the print, and the stroboscopic camera for Starjet characterization. Now, why do we need the stroboscopic camera for Starjet characterization? Because we know that in multi-material printing or any kind of additive manufacturing printing, we want to present a sustainable approach. But the sustainable approach will not work if the products we are producing from our additive manufacturing does not comply to the needs or to the requirements that we have. And in such cases, often there is more waste generated than the profit from this technology. In order to ensure this sustainable manufacturing, we make sure that our droplets that we have to print from the Starjet, where each droplet must be printed to have the continuity and the conductive tracks, we go through a thorough stability analysis of the Starjet droplets. In this case, we use the same multi-material printing platform, only focusing on the stroboscopic setup part of the platform. In this stroboscopic setup, I give you a quick overview of how we do it. We capture droplets from the molten metal droplets. So this you see in the black. In the center here is the molten metal droplet. Each droplet can be captured with our camera, and then we process it using an ISO standard technique, which was also developed here at Hanchikut. And we finally do some computation for the droplet volume and number of droplets. With this assessment, we are able to present the criteria with which we can see if or not the metal printing that we want from the start jet is within the limitations that within the criteria that we want. For example, we set the criteria here, and we want to make sure that there are no satellite droplets, which is often the case with printing technologies, most printing technologies. So by doing a thorough analysis of hundreds and thousands of droplets at different temperatures, reservoir temperatures, at different deposition frequencies, we find the temperature which has and the frequency which has the lowest coefficient of variation, and then we select it and go forward with it for creating for going for the hybrid printing of 3D electronics. So these are just a quick overview to show you how much assessment is done before the actual printing is proceeded. So in this particular hybrid printing technology, we have some technological stages. The first one consists of side-by-side deposition of metal on polymer. And as you see in this image, this side-by-side deposition of metal polymer requires the molten metal droplets to be printed consistently. Even if one droplet goes missing, we will have discontinuous line. And this means that if we try to build up the layer to go to the second stage where we build a next layer and on top, this will not function anymore. In this model, I just showed to you a USB plugged-in based model that we printed here. So the two traces coming out are something you can plug into a USB connector and then immediately verify the working of the thing. In the next technological stage, we have embedding of these metal droplets. So if we want to create three-dimensional structures, we want to embed these metal traces, which is also something which is was quite technologically challenging, because we have these bulk molten metal droplets printed on FFF polymers with deformation temperature of ranging from 56 degrees Celsius to 110 degrees Celsius. And in order to do that, we did some scientific assessment to see if we can print polymer channels, as you see here in this image, and deposit the droplets in those channels in a way that we have very low void formation around the channel and low coefficient of variation in the width of the printed tracks. And the final technological stage that we developed here was the vertical deposition of metal droplets for interconnecting via. In application exploitation of our StarJet technology, we have here selective soldering, as you can see here. This means that compared to the other technologies in the market, which present to you integrated electronic components, do not necessarily have direct soldering. So this is something you need to do as post-processing. But with the help of StarJet, we did some scientific investigations here to figure out the suitable temperature and volume of the droplet that must be deposited to have the necessary interface between the metal and the substrate. And here you see the top view of a SMD. And I think this was 0805 SMD, so very small SMD size with the bulk metal droplets. And this here is the side view of the same thing, where you can see the wetting behavior of the printed solder. Another exploitation is in the 3D printed electronics, as mentioned earlier. And for this, I just show you a quick overview of the assessments we did of the printed traces to actually form these conductive tracks. In the graph here, you can see the line width or the track width of these metal traces in red, and the resistance measured in blue. We did different orientations because FFF, as you know, is not a very fine resolution printing technology. Rather, it presents a crude or rough surface area. And therefore, this also is very important to make sure we are able to test our capacity in different orientations of the FFF printing. So these here on the top that you see are images of printed traces, which were formed by individual droplet deposition, and you can see how well the traces have fused to form this very smooth line, wherein you see the standard deviation is also not too high for the trace width. Of course, the orientation one would expect would have an influence on the trace width. However, no visible significant variation was visible. Same as the case for resistance, and it was possible to have resistance which was 12 times better than the nanoparticle inks from the state of the art. Next application I show you is the vertical via interconnections. This is suitable for connecting multiple layers. So here you see is a continuous deposition of droplets produced at 50% overlap. So each droplet was overlapping with the other droplet at 50%. In this particular image, you see the solder in the silver color, the polymer in the orange, and the epoxy in the yellow. So this grinded sample was done to observe what the metal on metal bonding looks like, because this was a layer by layer printing. As mentioned earlier, we print the substrate, we print the metal conductive trace, then we print the one layer of polymer with the hole, we print the metal, polymer, hole, metal. So this was done really step-by-step processing of additive manufacturing. And with this, you can see here how the fusion between the vertical droplets look like, and also how the fusion between the bottom part of the traces look like. The next wide range of possibilities are also in the flexible substrates, because we can print the lines from the SAC305 metals, as mentioned previously, with the help of drop-on-demand technology, and then we can selectively solder them with the help of the low melting point alloy. So this is a very good combination that was tested here, which can present a nice direct soldering of components for flexible electronics, as you see here on the image below. This is the green is the FFF printed polymer with some metal traces, interconnecting a flexible substrate with an LED on the top. Further applications which have been also tested are hybrid printed smart wearables, or 3D capacitors. Here on the top you see this is the capacitor printed on the FFF substrate. The capacitor was entirely printed from metal, as you can see here in the scanning electron microscopy image, how the metal droplets are deposited on top of each other, and this particular thing was 10 mm high, the capacitor plates. Or we can also have custom multi-layer electronics. So for example, this was a fully 3D printed with Starjet and FFF technology 555 timer circuit that you see here with the USB connector to give the power. Just overview on the hybrid printed smart eyeglass model. In this, we created an eyeglass arm which was customized to the customized shape, with a proximity sensor and a PCB connector here, 2-layer connections, and these were connected with the help of the Starjet technology, and able to successfully detect the chewing capacity of a person, because these sensors are near the eye, so there is a temporalis muscle, and this was able to detect the movement of the temporalis muscles with the help of these proximity sensors. Another custom design multi-layer electronics that we tried, as I shown previously, was the bunny chip model. This was nothing but a 3-layer structure where we had 2 layers of metal and 2 vertical interconnects. So in the blue here is the first layer with 1 layer of metal. The second one consists of the more complex structure where you have a more complex conductive layer and the 555 timer circuit. You have the resistors, the capacitors, and LEDs already included in this particular part, and then a covering polymer layer. We did a new method for presenting how we do the interconnection, because everything was done in one printing run. So there were no additional reflow soldering or nothing, but it was simply made with the help of the starjet. And this is here what we show, where some of the tests done to see how the metal interconnects with the surface mounted devices. Another application exploitation is the hybrid. In the hybrid printing is, as you see here, is a industrial connector. This had a custom 3D design for the polymer base that you see here with a vertical interconnect hole. There were some status indicator LEDs. There are some solder layers, so conductive tracks, a sensor ICE, and embedded solder layer. So this is the top view of the print device. And this year we showcased it in different messes, how this particular interconnect works. And this could provide us with online monitoring with web servers with integrated temperature sensors. And with this entire thing, I would like to thank you for your attention. It was not a long presentation as previous ones, because I would have to leave in 20 minutes. However, I want to welcome you to ask any questions that you would like to in these times, so I can answer them for you. Thank you.
Yeah, participants, kindly unmute yourself and ask the questions if you have to Dr. Zeba. If any questions, please, participants may ask the questions. Participants, if any questions, please feel free to ask.
I think there are no questions.
Hello, any questions?
No questions.
Sir, no questions right now, sir.
Excuse me, one question.
Yes.
So, what is the efficiency of this 3D printed components when compared to the traditional PCB boards?
Efficiency in terms of what? So, which particular element are you asking for?
Performance.
The
You showed a spectacle. I mean, a printed PCB to measure the and movement of chewing something. You told no the patient's chewing capacity something. So how efficient it is in measuring that? If there are information with you.
I mean, so the efficiency we measured of the printed parts in terms of different things, for example, to see whether the resistance of the tracks are low enough, to see whether we have the similar performance as copper traces on PCBs for any kind of crosstalk behaviors or something. But the efficiency of the performance of this particular connector was as similar as you would expect for a printed circuit board, because this is this requires certain connection which with amount of resistance that is needed, and this was sufficiently provided with the tracks that were printed. So the efficiency in terms of performance would be similar.
Thank you. Thank you.
Davis, Davis, thanks for the question. Efficiency in like 3D printing, if I Dr. Zeba can correct me, but efficiency can be measure in different, I mean, for different kinds of things, like as Dr. Zeba mentioned about the performance, is how your CAD model is getting translated into the reality. So that is one way of performance we can say, or performance from geometric translation point of view. We can say functional point of view, what functionality for which we design a component and how after printing it perform that particular functionality. Let us say 3D printing, if you are doing for some assembling, gear to gear fitting, and then after printing how well they are in tolerances and performing that particular function of motion. So we can measure that also. We can say the performance from compliant mechanism printing point of view, if you people do it, and that compliant mechanism performance also we can measure. And compliance or performance from the surface finish point of view. So that also we can measure in terms of some efficiency parameter, how that is translated. And performance from the energy point of view, from efficiency from the, energy point of view, efficiency um, from the material usage point of view, how much material is being used. Almost it is matching very close to the ideal condition, because in 3D printing there is a zero waste, but in case some support structures are needed, then some waste is there, so we can measure the efficiency in that particular sense as well. So even efficiency, we have to relate it to what parameter it is, okay, or what context we want that particular efficiency. Hope I clear a few of the things of yours, right, David?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, yeah.
Thank
And
you. Thank you so much.
particularly, the group of Dr. Zeba and Professor Ju, they work on the embedded things, printing and all those. So Dr. Zeba can add further onto it, like how they can measure all those performances in the 3D printing and further extension.
Thank you so for explaining the things here. Yes, so currently we are focusing on comparing our results with 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 itself. So in the sense that we want to first of all see whether or not the printed traces can be within the tolerance that you have in terms of consumer electronics, the things you have there, or whether the resistance of these traces are within those tolerance, and even if they're embedded, whether this varies. And also additional to that, we do some industrial reliability tests. For example, if you want to make a product or technology or push it into the application field, you have to present some proof of concept tests, such as very common test for 3D printed electronics is an 85-85 test. That means you have your model, printed model, you keep it in 85% relative humidity and you put it at 85 degrees Celsius temperature, and this is a chamber where you do live testing of the printed part. So this is very then you do the scientific investigation to analyze what part breaks, or whether or not it breaks, or whether it can complete 1,000 cycles of run, which takes weeks to finish. So these are some of very elaborate tests that we do to create some performance metrics here. And with this, we are able to identify, okay, which polymer and metal combination works, and which polymer can go up to even higher temperatures. For example, for automotive, you would need 125 degrees Celsius performance. So something like that. So there are different criteria, and currently we are trying to do it step by step to see which material portfolios we can present for this hybrid printing of polymer and metal. Because You do have it in terms of dielectric printing, but even in that field, currently this industrial tests that I mentioned, 8585, they suffer. The printed electronics, they suffer from it because the inks, they need this adherence to the substrate, which could break, or the ink itself can break under this humidity and temperature. And these we were able to have some successful results with some materials. However, some materials could not sustain the 85 degrees Celsius because polymer printing is with FFF. You have a nice portfolio, but to create the higher temperature stable materials such as PEEK or PI, we need to test these adhesion things with the metal traces. If that is not possible, then we don't go forward with the combination. So these are some of the tests that we also do additionally, addition to the application direction that we follow.
Yeah, thank you, Dr. Zeba, for the more insights on this. And if any questions further, a participant can unmute. And there are few questions from the a few things like the participants need is further maybe for networking. They need your contact details and all. If you don't mind, then I'll share with all the participants that.
Sure. Thank you so much for
And
this
also,
opportunity.
yeah. This is also a networking platform, like we see, like many focus groups are here. They may be wanted to connect to you. Okay. So I'll share the details of Dr. Zeba with the participants' email ID particularly.
Yes.
So Dr. Zeba, thank you for the insights on the activities at Imtech Germany, and it was nice demonstrating like what are the capabilities and all those systems that you are doing. Thank you very much.
Yep, no problem. Thank you so much for inviting.
Yeah. So,
and just one last comment that there are always these possibilities for researchers to do some collaborative work here. So you can check that website or another other websites with which you can try to do 2 years or 3 years research here. So this is also something which it's very much followed upon.
Yeah, thank you. And I think Dr. Suhas has joined. Dr. Suhas, you want to say something?
Yes, it's pleasure to see Jeba once again.
Hello, sir.
Yes, कैसे हो?
अच्छा है, sir.
Chalo. I was today with Kiran for some kind of work, but now I am on the airport moving towards Delhi. And it's pleasure to see you once again. Chalo.
Thank you, sir. I will call you separately.
Yeah. Chalo. Yeah.
Okay.
Bye, everyone.
Bye. Yeah, thank you, Seba, and thank you all the participants. We end this today's session quite early from the scheduled time. We hope so. We'll have some kind of a makeup for this particular time through some other supplementary material which will be shared with you. Thank you very much to all the participants. Okay, and see you see you tomorrow for the first session at 6 p.m. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.